So many of you have asked me to do an example of a calculation of forces between wires. So here we've got 3 wires. One is going into the page, one has current coming out of the page, and another has current going into the page. They're all separated by this distance, 0.01 meters, okay, between the first 2 wires and the second 2 wires. So this R is the same in both cases. And each wire is carrying 5 amps. And there's a 45-degree angle here between this vertical line and this distance off to the side to this other wire there. And the question is asking for what's the force per unit length at this wire here. And we know that wires carrying currents that are placed near each other will basically exert forces on themselves. And what we know is that when these wires are pointing in opposite directions, like this one is going out of the page and this one's going into the page, they're going to basically repel each other. They're going to push against each other. If current is going in the same direction, they're going to attract each other. So let's work this out. How can we figure out what the force per unit length is on that central wire there? So here's the steps that we're going to go through, all right? So first we're going to sketch the forces. We're going to get a rough idea of what the forces are, how they point, and what the resultant vector should look like. This is just approximate, we're eyeballing it, so we have a rough idea of what to expect for the answer. Next, step 2, is we're going to calculate the force per length between these wires. Since R is the same distance in both cases, and since everybody's carrying 5 amps, once we calculate it for this one, it'll be the same magnitude for this one. So we're just going to use a magnetic force per length equation, and we'll calculate that magnitude. All right. Then the third step is going to be this. Now we've got to do the vector addition, and we can break that down into different parts. All right, parts A, B, and C. The first part is we're going to take the 2 forces. There's going to be a force caused by this wire on the central wire, a force caused by this above wire on the central wire. We're going to take those 2 forces and we're going to break them down into X and Y components or parts. Next, we're going to add all the X parts together and we're going to add all the Y parts together. And then finally, given that total X and total Y, we can get the resultant vectors length and angle. So let's begin by sketching the forces. Let's take a look at it here. So as I said before, because these 2 currents are going in opposite directions, these guys are going to repel each other. So this wire here is going to exert a force pushing this wire away. That's given by this red arrow here. Okay? Now this one here is also going to push on this central wire, and that's drawn here as this force. It's going to be exactly equal in magnitude as this one here, because remember the wire currents are all the same and the distances are all the same. The only thing is that this one's pointing in that direction and this one's pointing in that direction. So we've got something like that. Now if I want to graphically add the vectors to get a rough idea of what's going on, I just pick one of the vectors. Let's say I pick this one, and then I line it up at the origin over here. So I take that vector and put it there. And then what I'm going to do is take this second vector and take its tail and line it up with the tip of the first vector. So I add them in a chain. So I get something that goes like this, and then something that goes like this. And then to get the resultant vector, I just start from the origin and draw toward the end of the chain. So I get a resultant vector that looks something like that. So we should get some force that roughly goes like that. That's what we're expecting here. And that makes sense, right? Because these guys are kind of pushing off in opposite directions, and so those parts opposed to each other are going to cancel, and we're going to get something summing in that direction with roughly that angle there. So that's step 1. We're going to sketch the forces, so we have a rough idea of what to expect. The next part is, let's just get the magnitude of those forces, okay? So we had a force that was going off like this. We had another force that was going off like this. What's the magnitude of that? Well, we're going to have to use this formula here. So this is going to be given on your formula sheet, or you can write it down however you want. The force between 2 wires, one carrying current A, one carrying current B, a length here, and this is 2 pi r, where r is the distance between them, and mu naught is the permeability of free space. It's just how easily the magnetic field goes through space. That's a constant we'll always give you. But here what we're looking for, and what the problem is asking for, is the force per unit length. Well, that's no problem. All we do is we divide both sides by length, and then we get this down here. So now here is what we're going to do. We're going to calculate this quantity in the box, and we're going to put in the values. So mu naught is just this. That's mu naught. That's a constant. We'll give it to you. The current in wire A is that, 5 amps. Current in wire B is the same. It's 5 amps. Down here, we've got 2 pi, and this is r, the distance between them, 0.01 meters. When you plug all that in, you get 5 times 10 to the minus 4th newtons per meter. And so that is the length of the red vector, so to speak. If I go back here, this vector here, I want to know its magnitude, and its magnitude is related to its length. That's what we just calculated. So we're calculating vectors that are going to represent the force per unit length. So that's going to be a quantity, but it's also going to have a direction. So it's a vector. So this is what we're going to get. All right, now we're going to go to step 3. Step 3 is break down everything into x and y parts, all the forces. So what I've done here is I've drawn the situation with the 2 red vectors. So I've got a red vector here, I've got a red vector here. We're going to break everything down into x and y parts. And so if I look at this one here, this one is just going directly in the y direction, down. It has no x component at all. So I don't have to do anything to break this guy down. Okay. On the other hand, this one is tilted at 45 degrees. If I just make sure that this angle is going to be matched by that angle. So this one's tilted at 45 degrees, so it's going to have an x component and a y component. I need to know what those are. So these little dots are basically showing all the different parts that we have. We've got a negative y part from this red vector, and we've got a positive x part and a positive y part from this red vector. So I'm going to group together this y part and that y part to get something like that. Those are going to add together. And then here I only have an x part, and that's going to be like that. So for our resultant vector, it's going to come from these things right here. Okay? So I'm going to add together these two and get a resultant y, and then that's my resultant x. So these are the parts that we're going to look at. Now I'm going to do calculations using sine and cosine. Okay. Part B of this is add the x parts together, add the y parts together. All right, so we calculated before that the force per unit length of this red vector is 5 times 10 to the minus 4th newtons per meter. And now what I want is this component here, okay? Because cosine is adjacent over hypotenuse, I've got to multiply it by cosine because this side is adjacent to the 45-degree angle. It's touching the 45-degree angle, whereas this side is not touching the 45-degree angle. This side over here is the opposite side. This side is the adjacent. So adjacent goes with cosine, opposite side goes with sine. So I take this magnitude, 5 times 10 to the minus 4th, multiply it by sine 45, and I get this. That's the length of this part right here. I take this 5 times 10 to the minus 4th newtons per meter, multiplied by cosine 45, and I get this. And that's the length or magnitude of this part here. Okay, good. So I've got the magnitude of this, I got the magnitude of this, and I know the magnitude of this going down because this is just the same length as this red one here, right? Because this isn't tilted, I don't have to break it down into anything, it's just got the same length as that. All right, so now I go over here, if you follow the little dots, and this one is going down with minus, because it's going down in the y, minus 5 times 10 to the minus 4th. This one is going up with 3.5 times 10 to the minus 4th. And remember, that is this component that we just calculated, okay? So now we add these guys together, point in the negative y direction, point in the positive y direction, and I get this total here, 1.5 times 10 to the minus 4th newtons per meter. That's the net y. And now for the x, I don't have to worry about anything because there is no competing thing. There's only one part that's going in the x direction. That's 3.5 times 10 to the minus 4th. So we get that. So now let's get the resultant vector. Let's do this. Okay, so that's this part. All right, so if I zoom in on this, it's kind of small print, but let's take a look at it. I add these two guys together. That's what I just did. And we said on the previous page, 1.5 times 10 to the minus 4th. And it's actually pointing down. I should put a little negative sign there on it. There we go. Sorry about that. And so that's my negative part, and this is my positive part that we just had. Okay? And so now what we're going to do is we're going to just basically add these guys together. So this is the component that we got in the x direction. This is the component we got in the y direction. It was pointed downward. Now to get the length, I've got to take the x total and square it, the y total and square it, and then put it under a square root. And if we do that, we're going to just use the Pythagorean theorem to get the length of this guy in the red here. And when you do that, you crunch down all the numbers, you get 5.89 times 10 to the minus fourth. That about makes sense. That sounds roughly correct. That is a little bit bigger than one of the individual red vectors that we got before, but that makes sense because we're adding two of them together, okay? And now we're going to look at the angle, and how do you get the angle? Well, the angle is this angle right here, theta, and we get that by noting the length of these different sides. And now what I want to do is say the tangent, which is the opposite over the adjacent, is this opposite over this adjacent, so I can set up this equation here. And in order to work this, what I do is instead of taking the tangent of an angle, I take the arctangent of a ratio. So I put 1.5 times 10 to the minus fourth over 3.5 times 10 to the minus fourth. I basically do that, the arctangent of that, and I get the angle theta. I get 23 degrees. So now the resultant vector looks like this. It's got an angle of 23 degrees, and it's got a length of 5.89 times 10 to the minus fourth newtons per meter. And remember, this agrees with what we had before when we went all the way back here to take a rough look at what our resultant vector should be like. It looks roughly like that. It's going to go in that direction. And so that roughly makes sense, and it seems to agree with the stuff that we've got here. So hopefully that was helpful to you. It's an example of how to add forces per unit length of wires in a vector manner. And this kind of thing will definitely be on the second exam. Hopefully that was helpful.